So we did a problem at the end of lecture. This is Wednesday, on Monday, and they remind me of titrations, kind of. So what I mean is I take up information from the paragraph and I put it under the species it applies to. So with regard to hydrogen, let's see, I'm going to find hydrogen. We'll say V is equal to 125 liters, which is a lot of volume, a lot of hydrogen gas. Also, the temperature of the hydrogen gas is 298 Kelvin. Well, that's nice. They didn't make me do Celsius to Kelvin. The pressure is 0.783 atmospheres. And it says that we have excess nitrogen, so excess. That's nice. Nice to know. And then the question in italics down here, how many liters of ammonia? So question mark liters. Question mark liters, or volume, or whatever. So we've been working with PV is equal to nRT, and do you see where we can actually use these three variables to knock out N, right? And then we can use stoichiometry to go from the moles of hydrogen to the moles of NH3. And then the other thing down here is with regard to temperature and pressure, it says that over here the ammonia, we're supposed to get the volume of ammonia, and it says the ammonia is at standard temperature and pressure. Do you guys remember what the temperature is for standard temperature?
0 Celsius.
It is 0 Celsius, yep, which is that 273 Kelvin. Do you remember pressure?
1.
Yep, 1 atmosphere, cool. And one more thing I'm going to jot down, because actually I'm going to use it to my benefit. Do you guys remember standard temperature and pressure? If you have this temperature and this pressure, exactly 1 mole, so I don't know how many sig figs you want to give it. I'll give it 5 sig figs, 1.0000 moles. Do you remember what the volume would be?
1.
Nope. It's that, I had that beach ball that I say.
Oh,
So,
2020, we're going
close. I looked at it because I usually get these numbers turned around. 22.414 liters. Yes. Okay. So actually, we are going to use this 1 mole at standard temperature and pressure, and I'll show you where it's going to insert in this problem. We wouldn't have to, but we're going to. It's a shortcut. If you are at standard temperature and pressure, then 1 mole for this gas, which will be ammonia, will occupy a volume of 22.414 liters. We're going to use that to run it. All right, so here we go. I'm not even going to make my little box here. We'll just pretend like the box is here. So we're after N from the hydrogen gas. So what's that?
Can you go back?
I can.
So
1.000 moles, it's hard to read, is equal to 22.414 liters.
All right.
Yeah. Okay, so first off is to solve for N, so we divide both sides by RT, so we get N is equal to PV over RT. And we're ready to plug and chug, don't forget your units. So N is equal to, the numerator, our pressure was 0.783 atmospheres, this is the hydrogen gas. The volume is 125 liters. R is going to be 0.082058. Units of R are liters atmospheres per mole Kelvin. And the temperature was 298 Kelvin. So then I always kind of tell you, let's see if our units cancel like they should. I have atmospheres and liters cancel, and Kelvins cancel, and I have the inverse of 1 over moles, which is the same thing as moles. So 3 sig figs, and you get a value for N. Wow, it's a nice, neat number, isn't it? So N is 4.00 moles of H2. That's our limited reactant. So we can use stoichiometry. If we start with our 4.00 moles of H2 and then use the balance coefficients, or the coefficient of the balanced equation, we're going to put what, 2 moles of NH3 over 3 moles of H2. So moles of H2 cancel with moles of NH3. The 2 and the 3 are exact, so we're still allowed 3 sig figs. So you're looking at 2.67 moles of NH3. Now I mentioned this a minute ago. Now we could, now that we have N, and we know that standard temperature, you guys said, is 273.15 Kelvin, standard pressure is 1 atmosphere. We could go back now with this N and plug it in. But instead, what I want to do is this. Recognize at standard temperature and pressure, 1 mole, exactly 1 mole, 1.000 moles, is equal to 22.414 liters. And we can take any equivalency statement and turn it into a conversion factor. So now if we pull in our 2.67 moles of NH3, put it over 1, how can we use that ratio to our advantage to get to liters? Yep, 22.414 liters over 1 mole. So it's kind of a special deal that I kind of wanted to show you. Either way, you get the same thing. 3 sig figs, and so that must mean you are looking at 59.8 liters of NH3. Okay. So this part, is this part 3? Yeah, part 3 lecture had 3 problems, and the next problem is even shorter. I'll show you what this looks like. It doesn't look shorter, but I'll show you why it is shorter. Let's go ahead and take out the information and put it under what it applies to. So H2, V is equal to 25.0 liters, and T is equal to 25 degrees Celsius, and P is equal to 1.25 atmospheres. So we're after ammonia, NH3, so V is equal to question mark, so in italics down here, how many liters of ammonia? And then it says, it gives me information about the ammonia. Now, here's where the catch is, a good catch. Notice the temperature of the ammonia is also 25 degrees Celsius, and the pressure of the ammonia is also 1.25 atmospheres. So the fact that the temperature and the pressure are the same means that actually we can use, how does that work? N over V is equal to constant. In other words, number of moles is directly proportional to the volume. That was Avogadro's law. So it's going to make it really easy. Okay, so since pressure and temperature are the same, we can use Avogadro's law. So in other words, we can use this relationship. This, you recognize the 2 and the 3 are the stoichiometric coefficients of NH3 and H2. Okay. Oh yeah, that's, they are the same to say that with this reaction, as long as that reactant, that product are the same temperature and pressure, you can translate it to volumes. So instead of saying 2 moles of NH3, you can say 2 liters of NH3. Instead of 3 moles of H2, you say 3 liters of H2, because they're directly related. All right, so now if we go back to our original problem, 25.0 liters of H2, put that over 1, and then all we got to do is bring in that ratio. So it's 2 liters of NH3 will be formed for every 3 liters of H2 consumed. So those were picked up from the stoichiometric coefficients. No uncertainty brought by the 2 or the 3, so we're still allowed 3 sig figs. Still a weird number, starting out like a pretty number, like 25.0 is a pretty number. 16.7 liters of NH3 is what would be produced.
But we still could have,
yes.
okay, like the long process.
Mm-hmm.
Okay.
Yep, it would. Yep, you still could have, definitely. That's a good point. All right. So this is just a caution. Don't be using that approach.
unless your pressure and temperature are constant, or it will not be good. Okay. This next topic for, I know a couple of you are signed up for Chem 2. This next topic actually becomes a player when we talk about volatility in gases in Chem 2. In general, it's the topic of what do you do if you have a gas mixture? Happens all the time. Oh my gosh, don't get me started. Because right now, we're breathing in mostly nitrogen, and 80% nitrogen, 20% oxygen. So we have a mixture of gases in this room. And I'll go ahead and kind of set you up for what that looks like, I think. Okay, so if my X's, 2, 3, 4, 5, 6, 7, 8, those are nitrogen particles. And here are my oxygen particles. Okay, they are, so I have 10 gas particles in there. They are collective. What I'm going to say is the pressure they bounce against the wall is collective. So actually, if I say I can do the pressure of the nitrogen gas, okay, plus the pressure of the oxygen gas is equal to the total pressure. Makes sense. They come out, kind of do their own thing. And that's kind of, when we talk about partial pressures, we're talking about the pressure of a gas that's in a mixture, kind of what it does in its own. And these would be partial pressure of nitrogen, partial pressure of oxygen. So here's kind of a neat thing from OpenStack. So we have 3 gases, they're different colors. We have the blue gas. We do a lot with units of atmospheres, but we did talk about pascals. This is definitely a good unit. This has to be kilopascals. So 300 kilopascals is the blue gas. 600 kilopascals, looks kind of purple to me, is the purple gas. And 450 kilopascals is the yellow gas. Now, in order for this to work, we're going to, on the last little image, you're going to see that it is, that cylinder has the same volume. So we're going to take all 3 of those gases, and it can be done, and transfer them to a common container, and by golly, all you got to do is add up 300 plus 600 plus 450, and you get 1350. Makes sense? That's assuming that, like I said, the volume, they go into the same volume and it's at the same temperature. Cool. I'm going to kind of talk you through the same idea. Instead of cylinders, we have these cool little glass things. Have stopcocks on the top and the bottom. They have a little pressure dial up here. These actually are going to be my component A, B, and C, and this is where I'm going to shove them when I'm done. Okay? So I'm going to show you that they're all the same volume, show you that they're all at the same temperature. I feel like I'm doing a magic trick. Here in a minute, when I transfer, I'm going to have a total number of moles, which will be actually the sum of the moles of these guys. One of the things in this lecture notes and some of my other lecture notes that kind of drives me nuts is I wish I had a little subscript T up here. Because that, to me, the sub T means total, so total pressure. Now, we could say the total pressure, no worries. According to PV equals nRT, we could solve for P. We could say that the total pressure is the total number of moles times R times T divided by V. And we could do that for each of these these component ones. So where the total number of moles here actually is the moles of A plus the moles of B plus the moles of gas C. Okay. Moles of A, B, and C. Partial pressure of A, partial pressure of B, partial pressure of C. For each of these individually, I could come up with an analogous rearrangement on the ideal gas law equation and say this: the partial pressure of A will be equal to the moles of A, gas A, and RT by V, B, and C. Makes sense, right? All right. So I'm going to go ahead and put a subscript T here for the total. For the gas mixture, we're going to have to take the total moles times R times T divided by V. So one of the things we can do now, and so a little math, algebra, kind of distributive property thing, is I can take this N sub T, this total moles, and I can substitute that quantity in there. And it looks like this. No worries. And then, I guess that's not the distributed part. The distributed part is to go ahead and pull out each one of these times RT divided by V. Make sure we're all on the same page here. Let me put my subscript T. So the total pressure, and you're like, well, that's no duh. But I'm trying to kind of, it's like a little proof to show you how that, actually it's Dalton's law of partial pressure. These people, these guys, come up with these like, oh, laws, and you're like, well, duh. That just makes so much sense. So the total pressure, now do you guys recognize that this actually is the partial pressure of A, this is the partial pressure of B, and this is the partial pressure of C. All right, kind of anticlimactic here, but we're going to bring down the summation operation. In other words, I'm going to put my little subscript T here. Total pressure, bottom line, it's kind of like I showed you up here on the board here in this room. The total pressure that's going to be exerted is going to be additive of all the pressures of the gases that's exerting any pressure at all. That's it. That's it. Dalton's law. It's the same Dalton that came up with Dalton's atomic theory, which I guess is pretty cool. I don't know. Okay, so, and it wouldn't have to stop with 3 gases. Here I have 2 gases. It could be 4, 5, 6 gases. But actually, we can use that to our benefit to work some problems. Okay. Okay. Oh, I know what I'm going to do here. This is kind of fun. Another little mathematical trick we got. Okay, so this is component A, or gas A, and this is applies to the total pressure. We can actually go ahead and take this divided by this is equal to this divided by this. That looks like this. I know it seems kind of strange. And let things cancel that will cancel. It looks weird that we have like 2 equal signs, but just bear with me. Notice that because of how we have it set up, of course, R's cancel. They're at the same temperature, they're at the same volume, okay? And so actually this distills down to this, where the ratio, and we're not quite done yet, there's one more form of this, but the ratio of the partial pressure of a component to the total pressure is equal to the ratio of the moles of A to the total number of moles. I feel like in Chem 1, I get my Chem 1 and Chem 2s mixed up, but this actually is the molar ratio. Did we talk about molar ratios before? Molar ratio. So all the molar ratio is basically, it's the component of interest divided by the total numbers of moles. So let me put a little subscript T's. Like, I think the T's are important. Oh no, I probably should clean up my slides one of these days. So in other words, if you want to know the partial pressure of a component, oh, I know, it's a mole ratio, actually it's mole fraction. Final answer. Mole fraction, maybe that'll sound right. Mole fraction, I'm pretty sure we did that. Okay, we did, I think so. We did too. We did solution concentrations in terms of mole fractions. Yeah, mole fraction, and it's like an X with a little subscript. Okay, good. So this is the mole fraction of A. This makes sense. So what its partial pressure is going to be is equal to its mole fraction times the total pressure, which is quite handy. Okay, so that actually is a form of, mole fraction. And this actually we would call X sub A. I think that's right. There's X bar sub A. Oh my goodness. I should have looked at this first, right? Yep, X sub A. Good. So, there we go. Partial pressure of A is equal to mole fraction of A times total pressure. Like I said, that just it pops out at me what that P is, because I'm like, there's too many P's here. Seems reasonable. Let's see how we can use that to our benefit in some problems. Well, we're going to be dealing with problems that are gas mixtures. So I think I'm going to go ahead and draw this up on the board here. So we have carbon dioxide, nitrogen, and neon. That sound like 3 perfectly good. And then I could do like X's, dots, and dashes for the 3 particles. Not drawn to scale. So we have CO2, 2.00 grams. N2 also. And neon also. But, all right. As we work the problems, you might be saying, well, grams are all fine, but here in a minute, one of our first thing is going to be to actually convert those grams to moles. Let's see, we got V is equal to 5.00 liters. And we have T, we're going to have to convert that, is equal to 15 degrees Celsius. And this isn't Dalton's, well, Dalton's law of partial pressure says that the total pressure is going to be equal to the pressure brought by CO2 plus the pressure brought by the N2 plus the pressure brought by the neon. And also we know that the pressure of anything, so I'll say piece of A, is equal to the mole fraction of A times the total pressure. So we're supposed to come up with the partial pressure of each gas and the total pressure. Those are kind of what we're gonna do for our use to get down the road here. There's probably a couple ways to work this. Bottom line, we're gonna have to do some of the background work that we have done earlier in this course. So we're gonna have to take those masses and convert them to moles. So starting with CO2, take our 2.00 grams of, and do you guys remember the molar mass of CO2? 44.01 grams per mole, yep. Geek. 1 mole over 44.01 grams. 3 sig figs, so the moles of CO2 looks like this. Talking 0.0454 moles of CO2. Nitrogen, we had 2.00 grams. What's the molar mass of nitrogen? N2. Yep, 28.02. Yep, very good. Eep. So 1 mole for nitrogen N2 over 28.02 grams, 3 sig figs, so you're looking at 0.0714 moles of N2. And I don't have neon memorized, but we had 2 grams of it. From the periodic table, we can pick it off, and it must have be 20.18 grams for 1 mole for neon. 3 sig figs. And you're looking at 0.0991 moles. What if I added all these together? What would I get? No, not 1. This might be a hard question. N sub T, our total moles. Does that make sense if I added them all together? So if I take each one individually, divide by NT, does this make sense? I get this guy, mole fraction. If I take the 0.0454 divided by NT, I would get the mole fraction. Oh yeah. So I can't remember how I wrote this. I think what we're going to see in the next slide is we're going to rearrange PV equals nRT. And we're going to solve for pressure, and we're going to say that the total pressure is equal to the nRT over V, because we were given temperature and volume. And then though, to get the individual ones, we're gonna use this. Does that make sense? Okay. So here we go. Adding them all together, your NT, total number of moles, is 0.2159. That's gonna be this guy right there. 2159. So, rearranging, PV equals nRT, solving for P, total pressure. So our total pressure would be the total number of moles, RT divided by B. Okay. So earlier in the problem, they gave us a temperature of 15 degrees Celsius. We have to convert it to Kelvin at 273 units. That gives us 288 Kelvin, and our pressure was ready, or sorry, volume was ready to go. 5.00 liters. So now we're ready to take these numbers and plug them into the ideal gas law equation, and it looks like this, where total pressure is equal to total moles, 0.2159 moles, times 0.082058 units of R, or liters atmosphere per mole Kelvin, times that 288 Kelvin. I usually put it over 1 so they can cancel with that. And the volume was 5.00 liters. So unit-wise, let's see, moles cancel, Kelvin cancel, and I got liters canceling. And this time I have units of atmospheres in the numerator of the numerator, which is perfect. 3 sig figs, because of your temperature and your volume. You're looking at 1.02 atmospheres. So that is your total pressure. That was one of the 2 things we were, one of the 4 things I guess we're after. Now we could actually do the same process 3 more times by putting the individual moles here. We really could come up with the same number. But we're going to use this approach, where X sub A is the mole fraction of A. So we'll pick on carbon dioxide first. The mole fraction would be the moles of CO2, which a few slides ago, 0.0454, divided by the total number of moles, 0.2159, times the total pressure, which we just came up with is 0.102 atmospheres. So we're good with 3 sig figs, 0.214 atmospheres. Moving on to nitrogen. A few slides ago, we got the number of moles of nitrogen, 0.0714. Again, divided by the total moles, 0.2159, times the total pressure, 0.102 atmospheres. 3 sig figs, I get 0.337 atmospheres. And last but not least, we have neon. So the partial pressure of neon will be the moles of neon, a few slides ago, 0.0991, divided by the total moles, 0.2159, again times the total pressure, which is 1.02 atmospheres. 3 sig figs, I'm liking 0.468 atmospheres. So without even taking your calculator, what would the pressure of all those partial pressures, what should it add up to be?
0.2159.
The pressure, no. Pressure combined should be the total pressure. Should be 1.02. Yep, should be. Yep, because that was how you got it. I think I have a check on the next slide. But you could convince yourself. Okay. Another problem. Let's see. All right, let's drag out the information in the paragraph below and put it above. So we have 150 grams of the dimethylhydrazine. So here's your dimethylhydrazine. So I'll say M instead of N. The mass is equal to 150 with 3 sig figs grams. And we know we can go from grams to moles just like that. Okay. It reacts with excess. So I'll put excess under my N2O4. And the product gases are collected. Now here's the deal. We'll look carefully. Make sure we have all gases. So these are all gases. So these are going to be banging around in the same reaction vessel after the reaction. So here we go. All of these, the T is equal to 27 degrees Celsius. Of course, we can get that to Kelvin by adding 273. And it says that our V, volume that's going to contain those 3 gases, is at the volume's 250 with 3 sig figs liters. So that sets up the problem. So we have a few questions. One is, what is the total gas pressure in the tank? So question mark P sub T. And the other one is, what is the partial pressure of N2? So question mark partial pressure of N2. So, yeah, the only thing, the way we're going to work this problem is we're going to take that mass, we're going to have to knock out the molar mass of CH3 quantity 2 and 2H2, knock out the molar mass, use it to get to moles, we can do that. And then, actually, I'm going to do something kind of cool. So, I bet I'll do it this way. So this one, you can get to moles of that, right? And then I'm going to use stoichiometry to get from moles of, because we have a relationship of 1 mole of the dimethylhydrazine will form, do you guys buy this? 3 plus 4 plus 2. It will form a total of 9 moles of product. Okay, so actually, our N sub T is, well, it's not N sub T, but we're going to use the whole 9 moles of product gases. I'll show you what that looks like. And then we'll have, we can get to the total number of moles, and then we can go ahead and knock out the total pressure and kind of go from there. So here we go, molar mass of that compound. Whoosh! Do you guys have this? Okay. So accounting for the carbon, 2 times 12.01. Accounting for the hydrogen, plus 8 times 1.008. For the nitrogen, we have 2, so 2 times 14.01. And so you're looking at a molar mass of 60.81 grams per mole. So we're going to use that to go from our 150 grams to moles. So our starting term is going to be 150 grams, and we're 3 sig figs, don't forget that decimal, times the molar mass of dimethylhydrazine, 1 mole over 60.10 grams. Grams cancel, we're left with units of moles of dimethylhydrazine. 3 sig figs, so a nice round number, 2.50 moles of that reactant. All right. And I kind of mentioned how we're going to, now, this is the shorter of the way to do it, but you could do this the long way, but you get the same number. So what I said a minute ago was we have 9 moles of product gases formed, but make sure, check for the G, gas, gas, gas. If there was an S up here, this approach would not work. So we can go ahead and say, based upon the stoichiometry, balanced equation, that we have 9 moles of gas produce 9 moles of product gases for every 1 mole, because the coefficient over here for the dimethylhydrazine is 1, for every 1 mole of CH3 quantity into H2. If you buy that, which I totally do, then we can go back to our, what we came up with, the moles of the dimethylhydrazine, 2.50 moles of CH3 quantity 2 into H2, and go ahead and insert that 9 over 1. 9 moles of product gases for every 1 mole of CH3 quantity 2 N2H2. So that's actually going to give us NT, or total moles. 3 sig figs, you're looking at 22.5 moles of product gases. So we can use this NT to actually come up with the total pressure. So here we go, which was one of the questions. Rearranging PV equals nRT to solve for P. Again, I would little subscript T here for total pressure, little subscript T here for total number of moles. Then plugging in total number of moles we came up with just a minute ago, 22.5 moles. The temperature was given in Celsius, so don't make a mistake of going with that. You have to convert it to Kelvin. This is an interesting one because we have no decimals in 27 degrees Celsius, and so we'll go with 273 units. So we'll go with no decimals, but you're going to get, your calculator is going to say 300, but you have to interpret that as this is rounded to the nearest ones, and this is ones, so we're allowed to our uncertainty begins with the ones. The volume was given, thank goodness. A big volume, 250 liters with 3 sig figs. All right, now let's plug. So our total pressure is equal to that 22.5 moles times R, 0.082058 units of R. With that value are liters, atmospheres per mole Kelvin. The temperature was 300 Kelvin, 3 sig figs. The volume is 250 liters, again 3 sig figs. Unit-wise, our moles cancel, our kelvins cancel, our liters cancel, and we're left with units of atmospheres, which is great. Looks like we're allowed 3 sig figs. So that's the answer to the first question. What is the total pressure? 2.22 atmospheres. Okay, so I was like, how do we get to the partial pressure of nitrogen? Well, let's see. We can get to the partial pressure of nitrogen using this. We need to get to the mole fraction of nitrogen, and actually we can do that by just going back to the balanced equation. The mole fraction of nitrogen, put it out like this, you buy this, that the total moles were 9, and the moles of nitrogen were 3. Okay? So that
we could have used the moles of just the stoichiometry.
That's true. Yes,
Okay.
we could have. Yeah, that would have been the same thing. You go back to that number of the moles here to the moles of nitrogen. Yep. So you're looking at 1/3 basically is the mole fraction of nitrogen. So the partial pressure of nitrogen will be that mole fraction, 1/3 basically. And that P, remember I've been adding T's to all my P's there. It just makes more sense. And we're going to take the mole fraction nitrogen times the total pressure. So it looks like this. The partial pressure of nitrogen is equal to the mole fraction nitrogen, 3/9, times the total pressure of all the gases. Exact relationship here, 3 sig figs. So you're looking at 0.740 atmospheres. There's no way to necessarily test that one. Unless you came up with the partial pressures of H2O and CO2 and saw that they added up to 2.22. I'm gonna double check something. Yeah, I think, oh yeah, okay. We're gonna skip skip the next problem, and instead of doing the next problem, because I get tips from my husband who's also teaching this class. And so actually bring your notes. We're going to cover that last problem because it pertains to your lab tomorrow. We're going to cover it in lecture tomorrow, or in lab tomorrow. So we're going on to the last part. If I can find it. Maybe. There you are. Non-ideal behavior. We see it all the time, don't we? But this is non-ideal behavior of gases. So in order to understand non-ideal behavior, you need to remember what we said ideal behavior was. So, or ideal behavior is something that follows the ideal gas law equation. And actually here in a minute, at the end of these slides, I'm going to introduce another version of this for gases that are behaving badly, non-ideally. Okay. So I think it must be coming up in my slides, but I'm kind of anxious to remind you. We said a gas is behaving ideally if there are two conditions. One is that the volume is negligible. V is negligible, the volume of the gas particle. And the other one is that there are no intermolecular bonds. Okay, which is kind of weird. So with that in mind, in general, the closer that a gas is to being a liquid, then the less ideal it is. So just to kind of remind you how that goes, we have our solids, liquids, gases, and here we have a lot of intermolecular bonding. Here we have intermediate intermolecular bonding. Here we have no intermolecular bonds. Here they have a lot of motion, not so much, and just a little bit. Okay, so the closer a gas is to becoming a liquid. So here we have a gas, and we're going to make it become a liquid. Now think of what that's like. So how do we get a gas to become a liquid? There's a couple ways to do it, but one of the things that comes in mind, we can actually cool it down. We can cool it down or squeeze it together. Increase pressure or cool it down, or both. So the closer it does this, then the gas becomes non-ideal in general. And how do you do that? You lower T, and you can actually increase pressure to make that happen. So the further the gas is from being in the liquid phase, the more ideal it is. So becoming non-ideal, and this is most ideal. I don't know. In Chem 2, we're gonna have to kind of dive into these diagrams. These are called temperature pressure phase diagrams because they have pressure and temperature on the X and Y axis, and because they show the three physical phases. That makes sense. So the way they work is this. We see a sector, they're kind of in sectors. A sector over here for solid, a sector here for liquid, and a sector here for gas. Now, pressure temperature phase diagrams have to be specific for a specific substance. This one is for water. There'd be a different one for carbon dioxide, a different one for anything. Okay, but let's just see how this would work. Pressure in kilopascals. So we would say that water boils at 100 degrees Celsius. Okay, so actually this must be my normal atmospheric pressure. So can you see right here that we have, here it's water, here it's gas, here it's water, here it's gas. This is my transition place, okay? And we'll talk more about that. But bottom line is, if I want to get a gas, what do? Well, I heat it up. The other thing to get a gas is I have relatively, this is pressures over here. The lower the pressure, the more it tends to be a gas, and the higher the temperature, the more it tends to be a gas. Okay, and just like I said up here, the closer you go from being a gas to a liquid, well, how do you get it to be a liquid? Well, you cool it down or you increase the pressure. All right, and these are the two assumptions I said a minute ago. So how are you likely to get no intermolecular forces, intermolecular bonds? Well, you have them going really fast, so high temperatures and low pressures actually. How are you going to get their size of the gas particle to be negligible compared to the container it's in? Well, have it in a container by itself, very low pressures. Okay, so that's consistent with kind of that phase diagram. So this was the modified ideal gas law equation I was talking about. You recognize the PV is equal to nRT. I'm going to introduce a few terms. So to the pressure term, we add A and B, actually, to look them up. They're like, I think they're called van der Waals. Yeah, they're called van der Waals constants for a specific substance. Of course, you recognize N and B, but we just have an extra N and B up there. Okay. So this term then corrects for the pressure being out of whack, and this term corrects for the volume being out of whack. Okay. So my point here overall is you have to switch gears to this equation if you are pushing the limit of your gas behaving on non-ideally. When is that going to be? It's going to be at low temperatures and high pressures.
You're gonna have problems.
I can't remember. You won't have to work a problem, but you might need to recognize that it exists. The van der Waals equation and what it is, it's a modified version of gases not behaving ideally. And you might need to honestly have a sense for what does it mean why would a gas not behave ideally? And again, it's your low temperatures and high pressures. So that's sort of general, but they're kind of fun. They're not too hard to work. Okay, and I said that these are optional, right? Well, good. So yeah, we'll have to go back and finish 4. And tomorrow's lab is short anyway. And it is lab, what did I say, 16. I think we talked. So